Welcome to this presentation on estimates with time series. We will discuss ergodicity, autocovariance function and cross covariance function in this lecture. Recall the definition of stochastic processes. We already saw it in the previous video. We will now take up ergodicity. To determine statistical properties need many realizations, but in reality we usually have one realization of the random signal. Moreover, we may not have information on the probability distribution function PDF. A random signal is said to be ergodic if all statistical averages can be determined from a single realization. For ergodic processes, time averages obtained from a single realization are equal to statistical averages. For ergodic processes, the estimates approach the actual statistical properties when sufficiently large number of samples are taken while evaluating the summation, while evaluating the estimation. In view of this, we assume our processes to be ergodic and we will calculate only time averages. We will also assume that we have sufficient number of samples and we will take the time averages to be good approximations of statistical averages. Now we will estimate the mean, which is 1 over 2n plus 1 into sum of small n going from minus capital N to capital N. Notice that there are 2n plus 1 entries here, so we divide by 2n plus 1. We use the symbol small m. For mean we used mu. For the estimate of that we use small m. M sub u denotes that this is the estimate of mean of u. Next is the estimate of variance. Once again the definition is the same. Remember to include the estimate of mean here in the place of mu, and it is given as sigma sub u hat squared. Let us now take up the autocovariance function of a stationary process. This is the definition that we had before, and its estimate is given by this summation and scaling by 2n plus 1, which is the number of entries in this summation. And notice that we use small r to indicate the estimate, whereas the actual value is gamma, and we are using L because it is a stationary process. Now let us take up an example. Suppose we have un that has only two entries 1 and 2. Find the autocovariance function, find the estimate, and recall the formula for the mean, small m sub u is given by this. So the mean you can see immediately as 1.5. So you can also use this formula. Let us now apply the formula for r sub uu of L, which is given here, and r uu of 0, that means L is 0, then you have u of k here also, and here also u of k. As a result it is uk minus mu whole squared, and k takes the values of 0 and 1, and when you substitute you get, for u of 0 you get 1 minus 1.5, so it becomes minus 0.5 whole squared, and for k equals 1 it becomes 2, so 2 minus 1.5 is 0.5 whole squared, so it comes out to be 0.5. This is r uu of 0. In the next slide we will use the same formula, but now we will evaluate for RUU of 1 and 2 as well. So let us take up RUU of 1. The formula remains the same, except that now we have to substitute k equals 0 and 1, and when you substitute k equals 0, it becomes u of minus 1, which is 0, you do not have to consider that. So we have to consider only for k equals 1, and I substitute k equals 1, I get this expression, and it becomes minus 0.25. I would want you to verify this. Next, RUU of minus 1, I made a mistake. In the previous slide I said RUU of 2. One can check that RUU of 2 will give 0. You only have to calculate RUU of minus 1. Then once again use the same formula, and then you get the value to be once again minus 0.25. I would want you to go through this calculation yourself. Here is the definition, whereas its estimate is given by this. You have to remember to subtract the mean of the corresponding entity uk minus mu. Here it is y of k minus l minus my. Because it is stationary, mean is constant, so we use my irrespective of the value here of the argument. The largest value occurs at a lag where the dependence is strongest, and as a matter of fact this concept can be used to detect the time delay. There is a problem in the book that explains this. In practice, of course, we use a normalized function known as the cross correlation function, which is defined as follows. In the denominator we have autocovariance function evaluated at 0 lag, that is the largest value of gamma uu and gamma yy, square root here, and in the numerator you use same uy of L, and this is denoted by rho uy of L. We will estimate the cross covariance function now. It is easy for you to verify this property. Instead of gamma we use R for estimate, and when you change the order the sign will change. Now remember what I told earlier, this second index should be a lower one provided this L is positive. Now if we take L to be positive, then what it means is the index of y is smaller. So as a result the index of u is larger. So if you take the index of y to be the current time, then because the index of u is larger, this will refer to future time. So this would mean what is the impact of future input on the current y, and as a result we see that that will be equal to 0 because the current output cannot be dependent on a future input. So we have this important relation RUY of L equals 0 for all L greater than 0, and that is because, as I mentioned earlier, when this L is positive you are talking about this index of y to be smaller than the index of u, which occurs first in this subscript. Once again, this video also has quite a bit of mathematical expressions. I would want you to go through this video once again. I would want you to go through the examples in the book. We would also give Scilab code. I would want you to execute them. I would want you to understand each and every step. If you do that, the implication of some of the definitions and approximations, estimate and so on will become clear. Of course, these are extremely important in the system identification problem. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.